Alright, good afternoon everyone. My name is James McKenna. I'm about to head into my 4th year of electrical engineering here at UC Santa Barbara. My graduate student mentor was Yuan Liu, and my faculty advisor was Jonathan Klamkin. The title of my project is the Thermo Electric Control Board for an Integrated Optical Beamforming Network. Imagine being able to download a full-length, ultra-high definition movie to your cell phone in just milliseconds. This is the potential of millimeter wave technology. Basically, this technology just uses higher frequencies to drastically improve data transmission rates. These frequencies that we're using are between 75 gigahertz and 110 gigahertz, which can just intrinsically is faster than the current standard of microwaves, which is 2.4 gigahertz. Another bonus to millimeter wave technology is that there's a lot more bandwidth available at those frequencies. Since we are using a higher frequency, this means the wavelengths are shorter. When you generate these wavelengths, they actually result in a more narrow directional beam, as you can see in this diagram. This is a millimeter wave beam, and then this is the old microwave beam. Although it is nice to have more power focused in one direction, it required a higher level of precision to steer the beams to where they need to be. So what our research is on is using photonic integrated circuit technology to create an optical beamforming network that can steer this beam precisely. So the general idea behind this, this technology is shown here. You take one beam of light and you split it into 4 different paths. The path all the way on the left is the most delayed path. The path on the right is the least delayed. By staggering the delays like so, you can actually form the beam at an angle that you can control with the delays, as shown by this angle. So how these delays are actually achieved is using a device called a ring resonator. Franklin did a good job explaining what ring resonators do, but the main application we're using them for is just to create a group delay when light passes through. A key feature of these ring resonators is that they're actually temperature dependent, so the delays associated with them can change if the temperature they're operating at changes. Because of this, we have heaters paired with each ring resonator, and these heaters just are basically using the simple concept of heat dissipation through a resistor in order to control the temperature of the ring. As you can see here, it's basically just a conductive contact, and it's a chromium heater, which is simply just a wire we run current through, and by doing so, generates heat. So my goal for this project was to control 64 independent current sources so I can control each ring resonator and their temperature. This control board has to be, ideally would be controlled through a computer and then can be tuned very precisely. So here's a block diagram of my control board. It starts with just a computer control, and using I2C communication, the data is transmitted to the microcontroller on the board, which then selects and controls a digital to analog converter, which then produces a voltage, which is amplified, and then eventually goes through the heater in order to generate, or to send current through the heater to generate the desired temperature. So the design of the amplifier was what I mainly was focused on. And this amplifier is just utilizing this common op-amp design, a non-inverting amplifier, in order to supply a large amount of power. So just from left to right here, we have the digital analog converter that produces a voltage between 0 and 5 volts. That voltage is then amplified by the operational amplifier shown here. And then once we have the amplified voltage, it is buffered through this transistor in order to supply the amount of current required. This circuit was designed to achieve maximum conditions of 30 volts across the output and 43 milliamps through the load, given a 700 ohm load. So when you set up the circuit like so, the output voltage you get is characterized by the equation shown here. Because of this, we chose the ratio of the resistors to be about 5, which results in an output voltage of 6 times the input voltage. And since the digital analog converter ranges from 0 to 5 volts, that means the output will range from 0 to 30 volts. So the next step was selecting the proper digital analog converter. We wanted the current sources to be precise within 0.01 milliamps. And to do so, we had to do some math here. And we know that the current is, via Ohm's law, is just voltage over resistance. And so the change in current is the change in voltage over the resistance. And just using the amplifier circuit equation shown and the equation for DAC resolution, I obtained that the DAC has to be at least 12 bits of resolution. The next step, once I had the design of the device, I wanted to build it and test it to make sure it held up to our standards. The two tests I ran were linearity and stability tests. For linearity, this simply means that when you change the input, the output varies linearly. So if you change from 1 volt to 2 volts on the input, the output should change the same as if you change from 4 volts to 5 volts. Doesn't matter where you're at, the same change should result in the same change in output. The next test I had to do was a stability test. I ran the circuit at maximum conditions and I wanted to make sure that over a long time nothing would get too hot or no components would stop working and result in a situation like so. So some results of the testing. This was the linearity testing. Here I just used a microcontroller to sweep the input voltage and to also measure the output voltage resulted in it. As you can see, the result was very linear. The equation we got was shown here, and as you can see, the slope of that was 6.02, so approximately 6, which was what we designed the circuit to do. The next test was stability testing, and for this I just put the circuit on max conditions, ran it for a long period of time, and I just monitored the output. And as you can see, it remained very constant throughout the whole time, with a maximum variation of 0.3%. So linearity test was successful and stability was successful. So the next step was to build the design in PCB software. This is the design I have at the moment. It's still in progress, but this is basically the general layout that it's going to be. Each one of these 4 quadrants is one current source, or four current sources. So there's a total of 16 on this board. These 2 things right here are the digital and analog converters. This is the microcontroller that controls digital analog converters, and the 2 things on the side are just connectors for wiring. Eventually, once I get this design all finished, I will order it and then solder everything together, and it will look like so. This was another Thermo Optical control board from a different research paper, but it's very similar to ours, and this is an example of what it will look like. So just in conclusion, my final step, as stated, was just to finish the design and solder the board together and do some final tests once we get the board in. So this control board will help us tune and optimize the integrated beamforming network, and if that is successful, then we will be one step closer to revolutionizing wireless communication. I would like to acknowledge my mentor, Yuan Liu, who helped me along the way, my faculty advisor, Jonathan Clampton, who unfortunately couldn't be here, but he was also helpful in group meetings, and also Wendy Ibsen, Jens, and the AIM Photonics program, and everyone else named. You guys were all a great help. Thank you.
Questions? I have a question. So where would the optical beam fit into your circuit board that you're making?
Okay, so